Okay, great. Okay, so temporal planning, constraint programming, quantum computing. I'm hoping there's something for everyone here. My name's Kyle Booth. This is joint work with NASA Ames and the University of Toronto. We have a lot of ground to cover, so let's get going. All right, so what is quantum computing? I can't spend too much time on this. Essentially, it's an alternative to classical computing. We have qubits, we have quantum phenomena, and quantum computing has, some theoretical results that it can solve problems more efficiently than classical methods. This has some implications in a number of applications, including cryptography and others. So there's a number of different ways of doing quantum computing, and in this work we study the gate model. What is gate model quantum computing? Essentially, it solves problems by creating a circuit of quantum gates. So you're trying to find a sequence of quantum gates that you run to solve the problem. To tell you what a quantum gate is, I'm going to show you an example quantum chip. So this is an 8-qubit chip where the nodes actually represent qubit locations. The edges represent quantum gates. A qubit state is actually the information that's held on a node at any given point in time. And then we also have the definition of a quantum gate, which is that it is essentially an operation on one or more qubit states at a time. You'll notice from this graph, our quantum gates only ever operate on 2 qubit states, okay? So a high-level summary of what essentially happens in gate model quantum computing. We choose a problem. In this case, as I'll say in the future, it's max cut. We determine the gate types that we actually need to solve that problem. And then what we're going to do is we're going to determine a sequence of those quantum gates. And that's actually the primary focus of this specific work. So we choose the max cut problem. The max cut problem is actually very, very well suited to solve with quantum computing, and that's because we need essentially just one gate type to solve max cut under an ideal situation, and that's the phase separation gate. I'm not going to get into any details on the physics of phase separations. We just have to know that they work, okay? And so again, we take our problem instance, which is a max cut problem instance, and we have a quantum chip. So each one of those colored edges actually represents a phase, a PS gate, as I'll call them. The color just indicates different durations. So a red PS gate might take a little bit longer than a blue PS gate to execute. So what do we need to do here, essentially? The first step, what we do is we actually map the node numbers in our max cut instance to unique qubit states on the chip architecture, okay? So you'll see I have nodes 1 through 7. On my chip I have qubit states 1 through 8. I have 8 because you actually have to fill up all of the qubits on the architecture with unique states. But I'm going to map the ones in the max cut instance with the qubit chip itself. And then what I need to do is I actually need to execute a PS gate on the chip for every edge I find in the max cut instance, okay? So we can see we have an edge connecting nodes 1 and 2 in the max cut instance. So I need to execute a PS gate between quantum states 1 and 2 on my actual chip. Okay, so without getting into the quantum physics, this actually shakes out to be a nice problem that we can study with planning and scheduling. So again, start with the instance. We do our mapping. One of the problems with near-term quantum computing is that our chip architectures lack complete connectivity. So you'll notice some of these nodes aren't actually connected. So if I wanted to implement all of the PS gates that the max cut instance is giving me, I can't. So I can do the first one, no problem. 1 and 2, it's on both of them. 1 and 7, however, aren't because they're not actually neighbors on the quantum chip. And then some sort of similar trend follows. So we can see we can't do 2 and 7. Most of them we can't do, so we can actually just do 2 of the PS gates out of the total amount here. So the solution in the quantum field is essentially they need to design another gate type. So now enter the swap gate. And what the swap gate effectively does is it moves qubit states around the architecture by swapping them between qubit locations. All right, so we have, again, our PS gates, they're the colored gates, and we also have swap gates, which are represented by black curved edges, okay? So I have qubit states 1 and 2 on adjacent nodes. If I activate the swap gate between them, they change places. Fairly simple. So before we couldn't apply PS 4 and 7 or 5 and 7. If we conduct 2 swaps at the same time, I want to highlight this. What we can do, as long as we're not applying multiple operations to a single qubit location at the same time, we're fine, right? So we can actually do these 2 swaps in parallel. So we can swap these values, and now you'll see that 6 and 4 have changed places, and so have 8 and 5. And now we're free to execute PS 4-7 as well as PS 5-7. Fairly straightforward. The total circuit duration is going to be the duration of one swap action, because we've done them in parallel, plus the duration of a red PS and a blue PS. So it kind of shakes out to be a nice toy problem. The biggest issue is quantum decoherence, and this is defined as the loss of quantum information over time. Decoherence essentially occurs when the quantum system interacts with the environment. It's irreversible. Essentially, it's a bad thing. We can do some error correction to mitigate it, but at the end of the day, it's still there. So what we want to do, it gets worse with time. So we actually want to minimize how long our quantum circuit takes. So we want to minimize the make span of our quantum circuit. And as a scheduling guy, this starts sounding pretty attractive to me, right? So the problem, determine a sequence of gates that achieve all of the PS gates we need in our max cut instance. The objective here is to minimize the make span of the resulting schedule. You can see in the graphic here I have initial quantum states 1 through 8, time is going to the right, and we have a series of PS gates, which are the colors, and then swap gates, which are represented by white blocks. So as far as constraints go, I mentioned it before, we have a capacity constraint on how many things can happen on a node at once, and we also have some, for the planning people, precondition and effect style constraints that we need to represent in scheduling, which might be a bit of an issue. So it starts to sound a bit like a planning and scheduling problem, and of course the group at NASA Ames has actually solved this with temporal planning last year. Essentially what they do is they model the problem in PDDL, and then they solve it on a suite of different planners. You can see we have an excerpt of the PDDL here, where the first line is showing us how we initialize the qubit states to be constant values, and then I've just taken as an example the details associated with the swap action, where we have a precondition and we also have an effect as well as a duration. So this is actually a benchmark that's been published on the NASA website. You can go there and play around with it with your own methods, and I would encourage you to do so. Some observations based on the planning paper was that temporal planning typically found solutions quite quickly, but then it struggled to improve upon them over time. I noticed that there's a lot of scheduling characteristics to this problem. So we have things like make span, we have gate durations, we have resource capacity constraints. So the contribution, or one of the contributions, is can we solve this thing with constraint programming? It gets a little bit messy, but that's something I like about these problems. So we'll dive right into it. For those of you that aren't aware of CP, it's essentially used to solve constraint satisfaction programs like NQueen, Sudoku, etc. It's got applications in scheduling, vehicle routing, and robotics, and it's a backtrack search with some sort of logic-based propagation going on. The challenges. Okay, so this is where things heat up. You take a planning problem and you want to solve it with a scheduling technology, and things get really hairy really quick, okay? Why is that? So I talk about in scheduling often we have some sort of fixed horizon that we have to deal with, and we want to schedule things within that fixed horizon. I don't actually know what that is, so I have to compute some sort of upper bound on the horizon to improve my scheduler. It turns out you can come up with a decent upper bound by looking at the number of edges on the max cut instance, the geometry of your chip, as well as the duration of the PS and swap gates. I'm sure this can be improved, and that's kind of a piece of future work. Another thing that's even more frustrating is you need to figure out how many times a swap gate is going to be used in the optimal solution and use that as an upper bound to your model, right? Remember, scheduling, as opposed to planning, where actions can be reused, we have to supply all of the tasks to the model and then reason over them, right? So I need to supply an upper bound to my model, reason over those to determine a schedule. So again, if I take that particular swap gate, for example, I want to know, in the worst case, how many times is this swap gate going to be used in an optimal solution, okay? And I call that the swap upper bound. Another pesky issue is how do we model preconditions and effects in scheduling technology? So swap gates, essentially, when a swap gate is activated, it changes the state of the system, so I need to model that somehow. To activate a PS gate, I actually need the system to be in some sort of state before I can even activate it. So these are preconditions and effects. We tried several CP models, a MIT model, and we kind of rested on this an event-based CP model that seemed to perform the best out of all the methods attempted. So I'll just go real quick over the variables. So we have a variable that represents our make span of the compilation, and then we start using these things called optional interval variables. So we use optional interval variables for swap gate actions. Note that these are available within CP Optimizer. They're essentially defined by a duration, some sort of window on their start time, and you can actually set them to be optional so they don't actually have to participate in the final solution, which helps us out with those swap counts like I mentioned before. So we allocate the upper bound swap of these to each swap location in the architecture. Okay, and again, we represent PS gate actions with optional interval variables too. And then we have qubit state tracking variables, where essentially we look to track the state of a qubit location after we've done something of interest, okay? And these are going to help us express those preconditions and effects constraints. So the objective function essentially is to minimize the make span, but we also have a tie-breaking criteria, okay? So the secondary objective prefers solutions that have less swap tasks overall. And you'll note in this particular expression we have this presence expression, and so the presence of a variable, of an optional variable, is 1 if it participates in the final solution and 0 otherwise. It's quite a nice rich expression that you can use when solving these problems. As far as the constraints go, so we have qubit initialization constraints, we have our make span definition, so it has to be at the end time of the last PS gate. And then we also have our capacity constraints saying qubits can only be used by 1 gate at a time. And then we ensure that each PS gate on that max cut architecture is scheduled exactly once. All right, so these ones aren't pretty. So we get to modeling preconditions and effects kind of in CP, and this gets a little bit hairy again. So what we've done here is that first family of constraints are essentially the effects on our X variables of the swap gates, all right? And you'll notice what I do is it's kind of a reoccurring pattern for these constraints. If a interval variable is present, then it must have some sort of effect on the values of those X variables, okay? And we use this structure for expressing these sorts of things on all of these constraints. So the second family is the effect of PS gate tasks on interval variable or on the X variables, and then we also have the preconditions of PS gate tasks. You can refer to the paper if you'd like to see that in more detail. So we try our CP model out, and it's competitive on the small problems, n equals 8. Here you can see, how does this work? All right, so we have this blue line. So on that Y we have make span, and on the X we have time. The blue line is our first CP attempt, and this orange line is actually our leading CP model, and the other lines are planners, and we can see that we're diving down and improving on make span with a similar trajectory to the planners, which is nice. So I was pretty hopeful. But it turns out when we take that n equals 8 architecture and expand it to 21 qubits, all of a sudden CP can't solve really too much, right? So it can't even find solutions for 60% of the problems, versus planning's finding solutions for 95 to 100% of the problems, and the planner solution quality is much better. However, like I said before, it doesn't improve much as time goes on. So that gives me an idea. Can we combine the two methods within some sort of hybridization? So what we do is we take the planner, we run it until some sort of termination criteria, we take the PDDL solution, translate it to a CP receivable warm start, which is not as easy as it sounds, and then we run the CP model for the remainder of the duration. So this is a graphic kind of illustrating that. So for this work, we use a naive half and half method. Future work would have us look at more complicated strategies for this. Okay, so how did it do? Pretty good. So on the y-axis, we have % improvement over the standalone planner. On the x-axis, we have clusters of different instances. So this cluster of 3 are results for 21 qubits. Okay, each bar represents a hybridization of a different planner. We can see that for POP-F, it improves by about 8% over standalone POP-F, which was nice. However, for TFD, we actually see a decrease in performance. And then you can also see in some cases the hybridization improves the standalone planning by nearly 50%, which is really encouraging. Now we can look at a detailed solution. So this is what temporal planning gave us. It has a make span of 22 clock cycles, as they call them. And we want to feed that into CP and improve it. So we do that. The make span after is now 19. You can see that it's not just rescheduling swap gates, because if we look at this PS gate action that's happening on locations 7 and 8, in the CP solution it's actually happening on locations 1 and 2. So once again, I want to stress this is a complete technique that, given enough time, will find the optimal solution, and it's really nice because we are seeing some improvement in the compilation make span. Some additional details. So I didn't have time to cover these, but we look at multiple compilation passes. So what if we want to apply PS gates to those edges more than once? We also look at more hardware-inspired constraints, such as crosstalks, where we further restrict how many qubits can be active at the same time within the graph, as well as initializations where The decision to initialize a qubit to a given state at the beginning is actually also a decision point for the model, which makes things a little bit more difficult. See the paper for further details. As far as future work goes, I just wanted to make the point that quantum computing from a physical standpoint is really complicated, and I've still yet to meet someone that can explain it to me well, but we can abstract a lot of these ideas and then use planning and scheduling technology to solve interesting problems there. I've also been able to demonstrate here that there's some value in linking AI planning with OR/CP, and then as part of future work, I mean, we can look at tightening bounds, we can look at investigating more sophisticated switching policies, etc. So that's about it for me. If you're interested in the concept of integrating temporal planning or planning in general with constraint programming, there is a workshop at CP 2018 that I invite you to submit a paper to. So this is just a quick plug, and that's my presentation. Thank you very much.
Thank you. So are there any questions? Oh.
Yep.
Thank you. I don't do CP, but from the people who do, I've heard that if you want to solve a large-scale CP problem, you don't do a backtracking search. You do something like LNS or whatnot. So I'm just wondering, do you think that would work as a way of getting sort of approximately good but not provably optimal solutions out of your CP solution or CP formulation?
Part of CP Optimizer in the default search is a large neighborhood search. So that's kind of how it gets to the performance it can get to. I did also investigate a bunch of different search strategies. So instead of just the default one, you can go for a multi-point. You can go for depth first. So I experimented on a lot of different parameters that way. Yes.
Can I do another question?
Yep.
What's the actual durations of the actions there? Because it looked like they were sort of fairly even-sized blocks in that schedule.
Yeah, so core assumption here is that the durations are integer valued. So we don't see any floating point durations.
Okay. Is there a big range of different integer values?
No, so I don't believe so. I have looked at some of the more real world numbers, and they do get a little bit messier than the ones that we've proposed. So that part of our future work is kind of trying to incorporate more and more of the actual real world constraints. This is just kind of a first crack at this particular problem. Yeah.
Okay, cool.
Thanks.
So, nice work.
Thank you.
I was curious, so the main motivation for making these short plans is to improve on the operational system, right?
Decoherence, yeah.
Yeah, so have you tried running them, like a long plan versus a short plan on hardware and seeing how it goes?
Maybe perhaps Jeremy could field that one, yeah.
So there is some real hardware out there. In particular, there's a company called Rigetti at Berkeley that has such a thing. Minh may be able to correct me. My last understanding is that they have a functioning 8-qubit chip, but that there was a plan to run some of the plans a couple of months ago, but that they were still having some problems getting the chip to function. So I don't know. Do you know, Minh, if they're able to run yet?
It's 20 qubit and 2 are not functioning. So we are trying to model with the latest.
Yes,
so we have one intern working this summer on actually running the plan on the actual chip. So hopefully we can report next year.
We don't know anything about the noise properties, really.
Yeah. Well, they're a mess, but IBM's chip is free to use right now. So
Yeah, I know that they have an API, and but I think they have about like 4 or 5 qubit.
No, there's a 16-bit one.
16 qubit working.
And they $10 million, you can get a much bigger one.
They
Okay, so
the latest news
at the end of this session, there is still a snack and some drinks. so maybe that's a good time.
So the answer is no, you haven't tried it yet, but you want to.
All right.
Let's thank the speaker again.
Thanks.